My name is Isha Perry, and here is my lab on the motion of a falling object. This experiment is based on Newton's second law in the instance of a non-constant net force. The purpose of this lab was to compare my observed tracker data of a falling inflatable basketball with two computational models to analyze which model more accurately predicts the observed motion. The first model did not consider the drag force, and thus F net was the weight force. Based on Newton's second law, the mass in the equation does not affect the ball's velocity in Model 1, and the ball will constantly accelerate due to gravity. This is seen where the red arrow points. The mass will cancel out in the velocity update formula. Model 2 does consider the drag force, resulting in F net being the summation of the weight and drag vectors. The differences between these two models is significant, as only one model displays terminal velocity, as we will discuss later. Here is the video and data from my tracker experiment. I tilted the axis to account for a skewed camera angle. At approximately 0.65 seconds, where the red arrow is pointing, the slope begins to linearize. Here is the mass of the ball, initial position, final position, and frames used for data collection. For the gravity-only model, I edited the starter code by inserting the mass and initial position of the ball from tracker. I also made the initial velocity 0 since the ball is dropped from rest. The drag coefficient is 0 as well, since this model assumes no drag force. The j-hat vector is a unit vector in the y direction, and I use this to calculate the weight force, which is F net in the model. I used Newton's second law to update the velocity and position of the ball. Running the gravity-only model, you can see that the slope never becomes linear, indicating that terminal velocity is not reached. The acceleration due to gravity is constant, as there is no opposing force. The model significantly overestimates the position of the ball to be over 6 meters in the negative y direction, while the observed final position was about negative 2 meters. For the gravity and drag model, I found the drag coefficient by comparing the final observed tracker position to the final computational position through trial and error. I changed F net so that it would be equal to the sum of the weight and drag force, with the respective formulas for each force shown right here. To visually display the magnitude of each vector, I set the length of the arrow to be equal to the product of the vector times 2 meters divided by the magnitude of the vector. The model shows that the ball reaches a terminal velocity at around 0.4 seconds when the slope becomes linear. Before 0.4 seconds, the velocity is decreasing at a faster rate since gravity has a greater magnitude than the drag force. Once the drag force is equal to the force of gravity and F net is equal to 0, then the terminal velocity is reached. Of the two computational models, this is the only model that predicts a terminal velocity. It's important to note that a terminal velocity is attainable by any object, however, not all objects will reach terminal velocity. This graph compares my observed data to both computational models. The model with gravity and drag aligns more accurately with my observed data than the model with gravity only, as seen on the left. This means the drag is clearly acting on the ball as it falls. However, the model with drag predicts a terminal velocity will be reached at 0.4 seconds, rather than approximately 0.65 seconds as it was observed on tracker. In an attempt to improve data agreement, I created a third computational model in this scenario that I slightly threw the ball rather than dropping it and calculated an initial velocity using the first two data points from tracker. On the right, this model is shown with the yellow line, and that mostly aligns with the gray computational and drag gravity model. This graph shows that this does not improve data agreement, so the cause of error is most likely from human and tracker error. Movement by the person recording the video and blurry frames when selecting the center of mass on tracker may have skewed the observed data. Additionally, the ball did move in the x direction, indicating a cross-directional force, potentially from environmental factors such as air conditioning. There may have been deviations in the measured mass of the ball and the length of the reference wall as well, which may have skewed the observed data on tracker. It's important to note that the terminal velocity will not change if the ball is initially thrown. The ball will reach terminal velocity faster than if it was dropped, as shown by the data from a computational model. However, in both scenarios, the velocity levels out to negative 2 meters per second. On the left, the ball is thrown down with a velocity of 0, negative 10, 0 meter per second. On the right, the ball is dropped from rest. As you can see, they both reach a terminal velocity of negative 2 meters per second in the case of an inflatable basketball. Thank you for watching.